Today we're exploring mathematical optimization, a foundational concept at the core of machine learning, deep learning, and modern AI. Mathematical optimization is the process of finding the best possible solution by minimizing or maximizing a function subject to a set of constraints. In formal terms, find the vector x that either minimizes or maximizes the function f of x, where x belongs to script f, the feasible region. X here is the decision variable. More on this in the upcoming slides. Note that the optimization problem can be either a minimization problem or a maximization problem. In mathematical optimization, we optimize the decision variables for an objective function. Suppose we want to minimize the total production cost of two products, A and B. We define the function f of x and y equals 5 times x plus 8 times y, where x is the number of units of product A and y is the number of units of product B. The unknowns in the optimization problem, x and y in this case, are called decision variables. These are the variables we can control, and their values determine the outcome of the objective function. In real-world scenarios, decision-making is rarely like this. There are constraints in real-life problems. We must work within constraints. For example, for the same objective function, there can be some constraints, such as x plus 2 times y must be less than or equal to 100. Also, x and y must both be greater than or equal to 0. That makes sense, right? X, which is the number of product A, cannot be negative. Similarly, the number of products B cannot be a negative number. These constraints define what values of x and y are allowed. So optimization in this context is find the values of x and y such that this objective function results in minimum. While we find that x and y values, we need to make sure that the constraints are satisfied. This is a linear function. It has two variables, x and y. This is not a good problem to discuss because in reality, the minimum of this function is found when x is 0 and y is also 0. That is, the business can minimize its cost by not acquiring any of product A and product B. Hence, x is 0 and y is 0. This example is all right for educational purposes, but really, to understand the essence of optimization, we should use a non-linear function. Before we take a look at a non-linear function, let us also discuss the definition of free and constrained variables. A free variable is one that can take any real number value, for example, x in the set of all real numbers. A constrained variable is restricted to a range, like x being between 0 and 10. Constraints like these are very common in physical and real-life systems, where negative or extremely large values may not make sense. So, in our constrained problem, x and y are not free variables. They are constrained because x and y can be only positive real numbers. Also, x plus 2 times y is less than or equal to 100, so x and y are not free. However, in the unconstrained version of the problem, x and y are free variables because they can take any values from the real number world. All right, we've covered the basics. Now, let's examine this nonlinear function. We are minimizing x squared, where x can take any value between 0 and 10. This objective function involves a single variable, x. But is x a free variable? No, because x is restricted to the interval from 0 to 10. It is not free to take any value. Therefore, x is a constrained variable. Let's draw the function f of x equals x squared, plotted against x. The minimum value of f of x occurs when x is equal to 0. As you can see, the curve is displayed only for values of x between 0 and 10. That's because x is constrained. It can only vary between 0 and 10. Now, let's change that constraint. We'll let x range from negative 10 to positive 10. Even with this new range, the minimum value of f of x still occurs at x equals 0. As x takes on negative values, f of x becomes large again. That's because the function is x squared, and squaring a negative number gives a positive result. For positive values of x, the value of x squared increases as x increases. So whether x is negative or positive, f of x grows larger the farther we move away from 0. When x ranges from -10 to 10, the minimum of the function f of x is still found at x equals 0. So minimizing f of x confirms that the lowest value occurs when x is equal to 0. Now that we understand how optimization works for a simple function, let's move on and explore different types of optimization. Let's talk about continuous optimization. In continuous optimization, the variable, whether it's free or constrained, can take on any value within a range without any breaks or gaps. Think of it like drawing a curve without lifting your pen from the paper. If you can move from one value of x to another without lifting the pen, it's a continuous function. Of course, with more variables, it's not just a line. With 2 variables, it becomes a surface, and with more, it extends into higher dimensions. But the key idea remains: everything is connected, and there are no jumps between values. In our example, we are minimizing x squared, where x can take any value between -10 and +10. Since the function is defined for every point in that range, and the graph forms a smooth, unbroken curve, this is a continuous function. That's why this problem is called a continuous optimization problem. Now let's talk about discrete optimization. Discrete optimization is a type of optimization problem where the decision variables can only take values from a discrete set, usually integers or specific listed options, not just any number along a range. In this example, we are maximizing the function 10 times x, where x must be one of the values, 1, 2, 3, or 4. After evaluating each option, we find that the maximum occurs at x equals 4. That's because 10 times 4 equals 40, which is the highest possible value in this set. If x equals 1, the result is 10. If x equals 2, it's 20. If x equals 3, it's 30. All of these are lower than 40, so x equals 4 gives us the optimal value. And that's a simple example of discrete optimization. Now let's talk about unconstrained optimization. You've already seen an example of this in our earlier discussion. In unconstrained optimization, there are no restrictions on the variable. That means the variable can take any value without limits or boundaries. For example, suppose we want to minimize the expression x minus 3 squared. Since there are no constraints on x, it can take any real number. This is what makes it an unconstrained optimization problem. Now let's look at constrained optimization. You've seen examples of this already. In constrained optimization, the decision variable must follow certain rules or limits. In other words, the variable is restricted. It can't take just any value. Here's an example. We want to minimize the expression x minus 3 squared, but this time we have a constraint. X must be greater than -2. This is what makes it a constrained optimization problem. Now remember, continuous optimization can be either constrained or unconstrained. For instance, when we minimized x squared earlier, we added a constraint that x must be between -10 and 10. The same goes for discrete optimization. In our earlier example, x was restricted to a finite set, 1, 2, 3, or 4, so that was a constrained discrete optimization. But we could also have an unconstrained discrete optimization where x is allowed to be any integer without a fixed list or boundary. These are just some of the important terms you'll come across in mathematical optimization. And that brings us to the end of this introduction to mathematical optimization. Whether the variables are continuous or discrete, constrained or not, optimization helps us make the best possible decisions. Thanks for watching, and stay tuned for more on how these ideas apply in real-world data science problems.